Okay, folks, this is the third and final lesson on this part of properties of derivatives. Okay, so I just want to remind us of something we saw in the last video. Within the proof of the sum rule, okay, so the derivative of the sum of two functions is equivalent to taking the sum of the individual derivatives, okay, and even the one with the constant times a function. We saw that in the process of proving it, we needed to use the limit properties. Okay, and in particular, in order to use the limit properties to, say, split up a limit, the individual limit had to exist. Now, in those cases there, those limits represented derivative functions. Okay, so in other words, the derivative needed to exist at those points. So since this seems to be an important characteristic, well, we'll be talking about it a lot. We'll give it a name. Okay, so what we do is we call this differentiability. Okay, so let's define that here. Okay, we say a function is said to be differentiable at x equals a. Okay, so here we're talking about differentiability at a point. Okay, if f prime at a exists. Okay, and let's just make sure we know what this means. Remember that f prime represents the derivative function for f at any point in an interval or in the domain, so this would be a specific point. Okay, so the derivative of the function at this specific point exists, meaning that limit exists. Okay, now that's good. However, since we often are talking about a function not only at one point, but perhaps over its whole domain or over a particular interval, we also talk about differentiability on an interval. Okay, and all that means is that it's differentiable, the limit exists, that derivative limit exists for all points in the interval. Okay, so we can also say that a function is said to be differentiable on the interval AB, okay, if the derivative exists for all values in that interval. Okay, so we'll say if f prime at x exists for all x in this interval AB. Okay, so it means if we took that limit of the slopes of the secants for any point in that interval, it would exist. Okay, now just a little thing one should keep in mind. Notice I'm using open intervals here. Since the derivative is defined as a limit, we want to be able to approach any point from both the left and the right. So that's why we keep it an open interval, not including the endpoints. Now sometimes we do allow flexibility, and we can talk about differentiability on a closed interval. Okay, but we have to keep in mind that at A and at B, we can only talk about one-sided limit. Okay, so let's take a look at what this might look like on a graph. So let's take an example here, and let's take a nice function, something that looks, polynomial. Okay, and if I take, say, this point A, okay, recall that that limit is just the slope of the secants approaching a particular point. Okay, so if I take from the left, these slopes of the secants, as I get closer and closer and closer, will approach the slope of the tangent. And the same thing should be occurring from the right-hand side. So as long as it's approaching the same number, as long as it's approaching the same slope, whether I approach from the left or the right, that limit is going to exist. Okay, and you take maybe even, I don't know, let's take a portion of some portion of a rational function. And again, you can make the same argument that as I approach from the left or that I approach from the right, eventually it will approach the same slope of the tangent. Okay, not the greatest of pictures. This looks maybe a little more like that point there. Okay, So we notice that these functions are all continuous. So it might be tempting to say that all continuous functions will also be differentiable. Okay, so what you should probably do now is just stop the video for a second and see if you can come up with an example that might contradict that statement. So are all continuous functions also differentiable? Okay, so shut the video off now and think about that, see if you can come up with a response. Okay, welcome back. Hopefully you actually did shut the video off and think about it on your own. Okay, and if you think of, if you go through the functions, this is what I hoped you would have done. You think about an exponential function, and you go, well, that looks like, there should be a nice slope of the tangent at any point, and you might take a square root function, and that looks pretty good. Okay, and here you might think of maybe a sinusoidal function. Okay, and you might think, well, that looks pretty good. Looks like I can, draw a tangent at any point. Okay. I hope, though, you might have thought of this function here. And this is what I would say is the most obvious example of a function which is continuous but not differentiable. Okay, and this, of course, is the function y equals absolute value of x, or if we think of it in piecewise terms, negative x if x is less than 0, and take a look at what happens at 0. As I approach from the right, we see I just have a straight line. Okay, and the rate of change of this line is 1. Whereas if I approach from the left, the rate of change of that line is minus 1. Okay? If I look at the individual components of the two branches, if I take the derivative of x and I want to evaluate that at 0, okay, if I'm approaching from the right, well, the derivative of x we found was just equal to 1. Okay, so this should be approaching slope of tangents equal to 1, which is what we expected by looking at it graphically. And if we take the derivative of negative x, well, that's just the negative of the derivative of x using our constant multiple property from the last video, and that's equal to negative 1. Okay, so as I approach from the left or from the right, I do not get the same rate of change. Okay, so this function here is continuous at 0, but it's not differentiable at 0. Okay, it's differentiable everywhere else. Okay, it's just two straight lines, but at 0, it's not differentiable. Okay, and you can think about other types of circumstances where you might not have differentiability, and it often has to do with something like a corner. Or perhaps, what about something that looks like this? A function that we will be looking at a little later on. Again, as I approach from the right, I seem to have a slope of the tangent that looks like this, whereas as I approach from the left, the slope of the tangent seems to be approaching a line whose slope looks like that. Not the same. Okay, this is what we call a cusp. So this is another way in which a function might not be differentiable. Okay. I want to take a look at y equals root x. Okay. Now here, this is maybe not the best example because I'm only going to be able to approach from one direction, but I want you to consider what's happening at 0. So I can only approach from the right. But as I approach from the right, I see that the slopes of the secants are getting steeper and steeper and steeper. It actually looks as though the tangent at 0 might be equal, or might be, the tangent itself, might be the line which is the y-axis. But what is the rate of change? What is the slope for a line like this? It's undefined. Okay? So these are the three ways we tend to see a function that might be continuous at a point, but not differentiable. Okay? So I'll give you here something where you can approach. What if this continued and did something like that? Okay? Just so that we can approach from the right or the left. So we see that as I approach from the left, I get the same thing, something that's approaching a vertical tangent. And the rate of change is undefined for a vertical tangent. Okay? So, one thing we're seeing here is that just because a function is continuous, it does not necessarily mean that it's going to be differentiable. So differentiability is a stronger condition than continuity. So having a limit is not as strong as being continuous, and being continuous is not as strong as being differentiable. So a question I want you to think about is, are differentiable functions automatically continuous? Okay, we've seen here that continuous functions might not be differentiable, but is a differential function necessarily continuous? Okay, we'll talk about that last time. So we have a few more things to say about differentiability, and we'll wrap up these types of examples, but we'll do that in class. Okay, so please get the work done for next class, and if you need to rewatch parts of these videos, please do. Okay, that's it for now.